In this lecture, we would clarify a fundamental measurement, what it really means. So the title of this paper is "What Does a Voltmeter Measure?" This is written by a distinguished researcher in electrochemical systems, and it was published in this journal. So let's move on. So what does the voltmeter reading really represent? Um, to begin with, you can get an idea that it represents the difference between energy levels of electrons in two different electrodes. So a voltmeter has two different leads made up of wires, two different same wires made up of same material or two different material, let's say. So, and then you stick in those leads to two different electrodes. So voltmeter reading corresponds to difference in energy levels of electrons. So then the next question is, what is the energy we are referring to? In your thermodynamics classes, you would have heard there are different kinds of energies, right? Internal energy, Helmholtz free energy, and Gibbs free energy. So what we are referring to in this case is Gibbs free energy. So why so? Because Gibbs free energy is the natural variable that is minimized to establish thermodynamic equilibrium when the corresponding free variables are temperature and pressure. What do I mean by that? So I do an experiment wherein I am controlling temperature and pressure. So typically this can be the room temperature and this can be atmospheric pressure. So when I do an experiment at a specific temperature and pressure, there are different choices of thermodynamic um, potentials that can be minimized. So corresponding to these variables, temperature and pressure, and let's say number of molecules, Gibbs free energy is the relevant thermodynamic potential that is getting extremized, in this case, minimized. So if you use different set, some other um, thermodynamic parameters, let's say instead of temperature and pressure, you use temperature and volume in a particular experiment, there is some other potential different from Gibbs free energy, which is going to be extremized and so on. So when we are doing an experiment wherein constant temperature and constant pressure is being maintained, so the relevant thermodynamic potential is Gibbs free energy. Is important to note. So, and then there is another jargon. Chemical potential is a term that is utilized in, let's say, chemistry and chemical engineering, whereas physicists tend to use Fermi level. So it is actually one and the same. So when you say Fermi level of electron in a electrode, it refers to the highest occupied level of the electron in that particular electrode, and it is the same as the chemical potential of the electron in that electrode. So this is the typical um, symbol that is being used for chemical potential and Fermi level. So what we are stating here is voltmeter reading, denoted by V, refers to difference in chemical potential of the electron. Um, so this corresponds to charge of the electron times the um, voltmeter reading. So this is indicative of difference in energy level. Okay, so that is the most important point we want to communicate. So why is this important, and in which context this becomes even more important is being elaborated here. Sometimes you may also hear another term called Galvani potential. This is very common in electrochemical systems. Galvani potential refers to internal electric field in the electrode. When you say there's an anode and cathode, there might exist an internal electric field. And this internal electric field is referred to as the Galvani potential. In some cases, voltmeter reading is really indicative of difference in Galvani potential. But in many cases, it may not be indicative of differences in Galvani potential. So in cases where it is indicative of Galvani potential, so voltmeter reading can be just this delta 5. This is the internal electric field. So that may be so, but that is not the case all the time. This is more restrictive a case, but what is often, not often, it is all the time correct is this interpretation. That is a voltmeter reading corresponds to difference in chemical potential of the electron divided by charge. If the two electrodes are made up of the same material, this can be, let's say, a platinum lead and another platinum lead, or a copper lead and another copper lead, then the difference in electrochemical potential is of the electron can be written in this manner. So this is a general definition. Okay, so whatever has been indicated, highlighted in red is the general definition for electrochemical potential. It is split up as two terms. This indicates the internal electric field. If the electrode is made up of the same material, this term is 0 because the two leads are made up of the same material. Two electrodes are made up of the same material, let's say, then that happens to be 0. So in which case, this simplifies to this term. And when you put this into this term, the voltage reading from a voltmeter just corresponds to delta phi, which is the difference in internal electric field or difference in Galvani potential. This is often not the case when the electrodes are not made up of the same material. So let us go to a specific case. It has certain additional complexities. Let's see also why these additional complexities arise. So sometimes you may have a sample. Let's say this sample is a solid oxide fuel cell. A solid oxide fuel cell is something that operates at a high temperature to facilitate conduction in the electrolyte. It's a solid state electrolyte. The temperature is rather high. It may be even 500 degrees centigrade or 800 degrees centigrade. This voltmeter will be at a room temperature. So this indicates TL, that is the room temperature. Temperature L indicates low. TH indicates temperature is high. So this electrolyte, which is the sample, may have two different electrodes on either side. On one side, you may have a platinum electrode. On the other side, you may have a gold electrode. Why is this the case? The electrode which you use depends upon a particular condition. Okay, the stability of the electrode you use depends upon a particular condition. In a solid oxide fuel cell, one side of the solid oxide fuel cell is under oxidative potential or very oxidizing atmosphere. The other side of a solid oxide fuel cell is under a reducing atmosphere. So not all materials are stable in all conditions. So you may choose a particular electrode depending upon whether the electrode is exposed to an oxidizing condition or a reducing condition. The overall point I'm trying to say is that this electrode, the nature of this electrode and the nature of the lead that is coming out of this electrode might be different. So here you have a gold electrode and the lead that is coming out of this electrode is also gold. This electrode is different, lead is different from the electrode that is present on this side and the lead that is being present on this side. Let us indicate the rest of the information that is presented in the schematic. This lead is platinum. This lead is platinum, and these two leads are copper. So, I mean, that is this solenoid, which is inside a voltmeter, is made up of copper. So, typically we use gold and platinum because of their inherent stability, and copper is used because they're relatively cheap, much cheaper compared to gold and platinum, and they're relatively stable in the environment that is inside a voltmeter. So the leads that is coming out of a voltmeter will also be copper. So we are not going into how a voltmeter measures its potential. That's not the point of this lecture. But we are just mentioning that there is a solenoid inside a voltmeter, which, and the material that makes up the solenoid is copper. So in this specific case, where the two electrodes are different, the difference in Galvani potential is not the same as the difference in chemical potential. We'll try to discuss this point in this slide. So we have the standard notation, that is the difference in chemical potential between, when we say AD, that means there is difference in chemical potential of the electron between electrode D or a point D and point A. So in this case, what are the 2 points A and D? That refers to this point, which is in the electrode platinum, and D refers to this point, which is in the electrode gold. So with this notation, we are referring to, again, a difference in electrochemical potential of electrons between two different points. Then, when we say VBC, this refers to the voltage difference between these 2 points. That refers to just the difference in Galvani potential, because between these 2 points, there is the same material, which is copper. And because these are two material, there is no difference in chemical composition. This term turns out to be 0. So when we talk about difference in electrochemical potential, the difference in electrochemical potential divided by charge will just turn out to be difference in Galvani potential. Let's first consider a simple case where TH is equal to TL. This temperature is the same as this temperature, and that can be just room temperature. In this case, there is no difference between the electrochemical potential between this point and this point, okay, because there is no difference in temperature. Therefore, there is no difference in electrochemical potential also. This is the same platinum wire, and this wire is made up of platinum. So because the temperature here and the temperature here are the same, we can say that the difference in electrochemical potential between this point and this point is 0. The difference in electrochemical potential between this point and this point is also 0. So this may happen, supposing you are making a measurement on a battery. This might be the case because the battery operates at the same temperature wherein the voltmeter is operational. But in some other case, especially in the case of a solid oxide fuel cell, TH is different from TL. The difference between electrochemical potential between this point and this point is 0 because it has the same chemical composition. This wire, that is platinum, is being utilized here, and the temperature is also same. Therefore, we say the difference in electrochemical potential between this point and this point is 0. And the difference in electrochemical potential between this point and this point and this point and this point is one and the same, because this point and this point is at the temperature TH, and both the wires are made up of platinum. So we can make this statement. Putting all these things together, that is this condition or this condition, into the definition of difference in electrochemical potential, what we can state is that the difference in electrochemical potential between A and D is the same as the difference in electrochemical potential of the electron between the points B and C. Okay, so we have just substituted this into these equations. So when you do that, what you see is that difference in electrochemical potential between A and D is charge times difference in um, potential between these 2 points. So this is a general definition, and it's an important point to note. But the difference in between B and C, what is to be noted is the voltmeter reading, which is VBC, difference in these two potential, is not necessarily just the difference in Galvani potential between A and D. Okay, why is that so? Because the composition of the electrode A and the lead that is coming out of electrode A is different from the composition of electrode D and the lead that is coming out of electrode D. Okay, so in this case, this term is no longer zero. Okay, so go back to what that term means. Okay, so our general definition of electrochemical potential of an electron has two components. There is this component and a component that depends upon Galvani potential or internal electric field. When this term is no longer zero, we cannot say that VBC is just the difference in Galvani potential. This is the main point we are trying to clarify. And what is the significance? Why do we need to address this topic at all? There are 2 points. One is that you have a more fundamental idea of what are you measuring. So it is always important to understand what is the meaning of a particular measurement. In this case, the meaning we are trying to assess is what does a voltmeter measure? We have related that fundamental measurement, the reading given by a voltmeter, to fundamental thermodynamics. So the meaning is being clarified here. In some cases, this interpretation of the voltmeter reading is simple. We can just say it is indicative of the internal electric field. This is helpful because many things in electrochemical systems, what is happening in the electrode, an intuition that you have garnered from electrostatics is good enough. Okay, so that intuition helps you in understanding what is occurring. So you should retain that intuition. But in some cases, especially when the composition of the two electrodes are different, the consequence of chemical compositional differences has to be understood. So the difference in chemical composition is well represented only by introducing this notion of chemical potential. That has to be clarified and understood and related to what is measured by voltmeter. And this is not an esoteric topic because often you use two different electrodes made up of two different metals because the condition at the two different electrodes are very different. In a specific case, with respect to solid oxide fuel cell, one is exposed to heavily oxidizing atmosphere, a gas atmosphere, and the other electrode is heavily reducing, again, because of a reducing gas atmosphere. So clarification of the voltmeter in terms of chemical potential differences have to be understood. Thank you.